Okay, here we go with our fourth video in chapter 20, one more after this. Okay, so what we're going to talk about in this video is the probability of making our two types of errors. So the first type that we'll talk about is the type 1 error, which is really easy to calculate. So the significance level of any fixed level test is going to be our probability of a type 1 error. So just in terms of that, the probability of a type 1 error is just equal to your alpha. Okay? So alpha is the probability that the test will reject the null hypothesis when the null hypothesis is actually true. So we're going to consider the consequences of type 1 error before choosing a significance level, but we'll talk more about that idea of choosing a significance level and what happens when you increase and decrease in the last video, the next video. Okay, so let's just get an idea of what this probability would be. Let's talk about the, hang on, I just want you guys to see the example. So we're referring back to that truckload of potatoes example. Where 8%, they were saying that 8% of the truckload of potatoes had blemishes. We were predicting, or we were expecting maybe more than the 8%, or that was what our test was showing. And I believe it was 47, in a sample there was 47 out of 500 potatoes that had blemishes. So, just going back to, okay, so this distribution here should show most of what we should need to understand everything, okay? So, let's figure out what we know. So the first thing is that our standard deviation, that was on that last slide that I had put up that we're looking at, that was the 0.012. Okay. After running a significance test, we're looking for the probability of our alternative hypothesis when the null hypothesis is true. So the probability that the proportion is greater than 8%. Okay. So I ran my numbers using my my standard deviation, my proportion here was 47 out of the 500. Which is about 0.094, okay? So using that, my standard deviation, and my null hypothesis that it was equal to 0.08, I get a p-value of 0.1251, okay? Which is definitely greater than or equal to my alpha of 0.05. This is going to tell me to fail to reject my null hypothesis. Okay, let's understand why. Well, if I establish 0.005, an alpha level of 5% as my cutoff, given this distribution would be centered at my null hypothesis of 8%. My then 5%, my upper 5% would lie at 0.0999. So all I did there was I inverse normed. I'd have to inverse norm 0.95 to get the upper 5%, with a center at 0.8 and a standard deviation of 0.012. Okay, which would give me where my 5% cutoff would lie. Okay, so you could see that anything to the left of that would be what we're going to reject. Just like that 0.094, that would be roughly in over there, that we failed to reject. Anything to the right of the line is what we're going to reject. So it would only make sense that that rejecting the null hypothesis would have to be the probability of creating a type 1 error if a type 1 error is rejecting the null when it's actually true. So in this case, our probability of creating a type 1 error would be the 5%. Let's talk about a type 2 error. Unfortunately, not as easy to understand. A significance test makes a type 2 error when it fails to reject a null hypothesis that is really false. The probability of a type 2 error is denoted with beta. It is much more difficult to assess the probability of a type 2 error as it depends on what the value of the parameter really is, and we don't know that. So the problem is that if you know that it's false, so a type 2 error says that you're going to fail to reject the null hypothesis, but it's actually false. So if the null hypothesis is false, that means you don't know what your actual parameter is. So there are many values of the parameter that will satisfy your alternative hypothesis. If you're just saying that you know that it will be greater than 8%, you have a lot of options there as to what the actual parameter could be to satisfy your alternative hypothesis. Because if it's a type 2 error, then your null hypothesis is false. That means that you know your alternative hypothesis would be true. So we have to rely on only one value. So we have to rely on a sampling distribution to be able to find our probability of a type 2 error. Along with the type 2 error, we talk about the power of a test. It is probably more useful than knowing the probability of a type 2 error, the power of the test, because that can help us also with a type 1 error. So we can calculate the probability that a test does reject your null hypothesis when an alternative is true. The probability is called the power of the test against the specific alternative. So the power of a test is the probability that it correctly rejects a false null hypothesis. When the power is high, we can be confident that we've looked hard enough. Our evidence is good. It's backing what we're saying. If beta is the probability that a test fails to reject a false null hypothesis, then 1 minus beta is the probability that it does reject a false null hypothesis. So in other words, the power is found by doing 1 minus your beta, which is your probability of a type 2 error. Okay. To be clear, and I will say this again in class, you are not expected to know how to create or how to calculate the probability of a type 2 error or the power. Okay, you just really have to know how to interpret the power and change the power accordingly. That we'll talk about more in the last video. So I did just want to go back to this potato problem to help us realize where a probability of a type 2 error would come from. So here's that potato problem. Here's that same distribution that we looked at before to understand what our type 1 error would be in this situation. So anything to the right of 0.0999, which was where we were at in our 5% significance level. So suppose we create a type 2 error. If we create a type 2 error, then we would know that our null hypothesis is false. We know that our actual parameter is not 0.08, okay? We would know that our actual parameter is somewhere greater than 0.08, but there's no way of knowing what it's going to be, okay? So we actually can't find a type 2 error unless we do know what the actual parameter would be. So just for argument's sake, and I'm just throwing this out there, it's not, it's just like kind of a made-up problem. Let's say that for some reason I was able to figure out that 11% of the potatoes had blemishes, okay? So now I know that my actual proportion, my parameter, is 11%. Well, what that's going to do is it's significantly going to change this distribution here, okay? It is no longer going to be centered at 8% because that's not, we know for sure if we created a type 2 error that can't be your center. That's not your actual proportion. Instead, our actual proportion would be centered 11. So we create a new distribution here centered at the 11% that for some reason we all of a sudden know that that is our actual proportion. So now we already ran a test at the 5% significance level and found that and we found that anything to the left of that green line, that 0.099, okay, was going to be where we failed to reject, where everything to the right of that line was what we were going to reject, okay? So if everything to the left of the line we are going to fail to reject, if we know that our null hypothesis is actually false, this now becomes our type 2 error, okay? So I can find out what that type 2 error is here by doing norm CDF, okay, from negative 999 all the way up to that 0.099 with a center at 0.11. And I will have a new standard deviation here because it is a standard deviation based on a sampling distribution. You could just figure it out here because that's one standard deviation, two standard deviations, okay? Or you could just plug it in. So you find it by your success times your fail over your sample. We'll stick with the 500, okay? That's going to give you a standard deviation of 0.014. Okay, so when I do that, I find that the area over here, okay, which is creating a type 2 error, is 0.2 24. I have it here. 83. Okay. Oops, there it goes. A little slower than me. Okay. So the probability of a type 2 error in this situation is going to be 0.2483. Now the power of the test, okay, the power of the test says that we correctly rejected a false null hypothesis, okay? The power of the test is going to be found by doing 1 minus beta, which was your probability of a type 2 error, which was 0.2483, okay? So the power of my test here is 0.7626, okay? Okay, so actually, no, that was right. This is wrong. Okay. Now, the power of the test, you don't ever have to find. You don't ever have to calculate the probability of a type 2 error either. The power of the test would just be told to you, but you do have to know how to correctly interpret the power of the test. So, again, the power is correctly rejecting a false null hypothesis, okay? We know we correctly rejected it, okay? So how we interpret it, if a power is near 1, it means that the test is very likely to reject a null hypothesis in favor of an alternative hypothesis when the null hypothesis is false. Okay? So a power near 1 says that the test is very likely to reject a null hypothesis in favor of an alternative hypothesis when the null is false. If the power is close to 0, it's just going to tell you that the test had almost no chance of correctly detecting a false null hypothesis. Again, if the power is close to 0, it's telling you that the test had no chance or almost no chance of correctly detecting a null hypothesis that was false. Okay, we'll take those quick notes in class next class, but that is the end of this video.